solutions of some differential equations. So an initial value
Professor.
Some value, let's say x sub 0, where my function is equal to some value, and maybe some of the derivatives are equal to some given values. And so this would be an initial value. Your problem is some differential equation with an initial value. So say you have a nth order, a e of order n, with these additional conditions. That would be called an initial value problem. So a differential equation along with these initial values is called a initial value problem. Sometimes it's also a Cauchy problem. For ODEs, we'll almost always call this initial value problem. Okay. When we're talking about problem, but usually for ODEs, it's called the initial value problem, except when we accidentally call it Cauchy problem, but it's an initial value problem for ODEs. So general solution. Linear combination of the basis of the vector space of solutions is called a general solution. And so if you, like in the very last problem, if I think r equals 0, r equaling 1, and r equaling 2, I think were the solutions. So if you looked at the linear combination of, well, e to the 0 is 1. So of 1 e to the t e to the 2t, a linear combination of those will give you any solution for that particular differential equation. A direction field determines the integral curves. Okay, so let me do this. So it's a word problem. Lots of words. Okay, so page 17. A radioactive material, such as the isotope thorium-234, disintegrates at a rate proportional to the amount currently present. If Q of T is the amount present at time T, equals minus RQ, where R is greater than 0 is the decay rate. If 100 milligrams of thorium-234 decays to 82.04 milligrams in 1 week, determine the decay rate R. Find expression for the amount of thorium-234 present at any time T. Find the time required for the thorium-234 present any time. Wait, that doesn't make sense. Wait 1 second. There's some words that are missing here. This is section 1.2. Okay, let me just see something. There's obviously a word missing here. Section 1.2. Problem number, what was this? Problem number 12. Okay, so there's some word missing here. Oh, okay. Here, wait. Okay, so I think I just misread it. So radioactive material such as the isotope thorium-234, okay, disintegrates at a rate proportional to the amount currently present. If Q of T is the amount present at time T, then, okay, that makes sense. Then the derivative of Q at T is negative RQ, where R is greater than 0, is the decay rate. Okay, so that does make sense. Okay. If 100 milligrams of thorium-238 decays to 82.04 milligrams in 1 week, determine the decay rate R, determine the expression for the amount of thorium-234 present at any time T. Okay. Found the time required. Oh, that's it. Let me just look at C, problem number 12C. Oh, okay. Find the time required for the thorium for the amount of thorium. For the amount of thorium. There it is. Now that makes sense. C, find the time required for the amount of thorium-234 present at any time T. Okay, so good. So let me do that. So let's do A. Let me get rid of this stuff. So some techniques I'm going to introduce in this particular problem, but they should be relatively obvious sort of techniques. We'll give a name to some of these techniques later. Well, it depends on if we start chapter 1 or chapter, whatever, the chapter on first order equations. Okay, so let's do this. So the first part, let me just list some of the data that we have here. So for part A, it says that you start out, okay, it says you start out, sometimes this computer has some mental issues. So the amount that you start out with is 100 milligrams. Okay. Next, after 1 week, so after 7 days, I have a choice, and I'll say days is my time. So after 7 days, I have 82.4 milligrams remaining. So it says that it decays at this, according to this differential equation. So dq over dt is minus rq. So I can write this differential equation as a differential form. And so let me write this as a differential form. Please note that one of the reasons we had a prerequisite of Math 263 because they gave you some practice with differential forms. I will maybe in a day or two give a quick review of differential forms right before we talk about exact equations, or maybe as we're talking about exact equations and integrating factors, so that either you learn that material or that you review that material. So I have the following differential form, that dq equals minus rq dt. Okay, so let me divide both sides of my equation by q. So dq over q equals minus r dt. Let me integrate both sides. And so this says that ln q is equal to minus RT, let's say plus C. Exponentiate both sides of my equation. So Q of T so Q of T. Okay, can we control back? So Q of T. Sorry, having some control issues here. So Q of T is equal to e to the C, I'll just call that C, times e to the minus RT. So we have that if I plug in 0, C e to the minus R times 0 is equal to, I believe, 100. And so I have that e to the 0 is 1, so C is equal to 100. Okay. And so from there I have that Q of T. That Q of T is equal to 100 e to the minus RT, or T time is given in day. And so I have that only 82.04 grams, I think, or milligrams remained. You start with 100 milligrams, and you did this for 7 days. So divide both sides of your equation by 100. Get control back. 0.804 equals e to the minus 7r. Take ln of both sides of your equation. Ln e to the exponent is just that exponent. Okay, so divide both sides of your equation by -7. Fighting with this computer. And so R is equal to ln 0.8204 all divided by -7. Okay, so that's what R is equal to. Okay, so now let's figure out B. Okay, so for part A, we just want to figure out R. part B, we want to figure out what the expression is. So, well, we're almost done. I had that Q equals okay, so let me write this down. So I have that Q is equal to, well, the amount we started out with, which was 100, e to the, well, whatever this is. Well, we have a minus this. Well, this is a minus here, so the minuses cancel. So 1/7 ln 0.8204 all times t. And so that's your answer. Now, of course, I can multiply the t and the 1/7 together, write those up as an exponent by the properties of logarithm, but e to the ln of anything is just that anything. So I can write this actually in slightly simpler form as 100 times 0.8204 to the power t over 7. And this is usually the way that they write these type problems in elementary school. So they usually write them where you have some base to some answer. Okay. Give me control back. Thank you. So that's your answer. Okay. Still no control. So for part C, I want to figure out the time it takes for only half to be present. Okay. Okay, so part C. We have I want to figure out how long that will take. And let me just check. Okay.
Professor, can you explain that step on part B?
Sorry. There it is. Let me look again. Let me look at this for 1 second. Section 1.2. Number 12. Oh, here it is, yes. Part C. See, okay, so for part C, because I'm looking at part C, it didn't make any sense now. So the amount, okay, here it is. Find the time required for the thorium, thorium 238 present, for the thorium to decay, here it is, to decay to 1/2. There it is, to decay to 1/2. To decay to 1/2. Its original amount. Okay, there. Now that makes better sense. Sorry, I was having some problems with the with this. Half its original size, original amount. Okay, there. Let's see if I can read that now. Sorry about that. I was having some problem. He applied. Oh, can you explain this step? Oh, the t to the half. Oh, okay. Yes, sure. Okay, so let's, sorry about that. That was just some properties of logarithms. Okay, so, and not that I really even needed to do that. So let's do this. So I wrote this as q to the t is equal to, okay, sorry about this. It's having a little bit of, computer's having a little bit of mental problems. E to the ln 0.8204 to the power t over 7. So I have this x, I multiply the t times the point times the 1/7 to get t over 7. E to the ln of anything is just this. So this is equal to 100 times 0.8204 to the t over 7. And that is, well, I could have left it actually in this form, but this looks simpler. Okay, let's see what the question was. Okay, good. Yeah. Okay. Let me do part C. So for part C, I finally have the full question there, is to see how long it takes until you get to half the amount. And so for part C, I want to figure out how long. Okay. And so let's try to solve that. So it's basically figure out your half-life is what they're really asking you for. And so let me just set this equal to 50. Equals 100, 0.8204 to the t over 7. I could have actually left it in this previous form. Doesn't really matter. Divide by 100. Take ln of both sides of my equation. Okay. Now, ln et in the exponent. Ln of this is just, well, so this is going to be ln 0.5. I can bring the exponent out in front. So this is t over 7, ln 0.8204. So let's solve for t. And so, I need another page. And so I have here that T is equal to 7 ln 0.5 over ln 0.8204. And that is your answer. You could plug into a calculator to get an approximate answer. Any questions about that? Okay. Yes, it's 12:50. Okay, so let me do problem number 5. Undetermined coefficients. So it turns out that the technique of undetermined coefficients is actually a fairly powerful technique. It is a technique that we will be looking at later in this course, especially for higher order differential equations. We'll be using this technique of undetermined coefficients. It can be used in a variety of situations. It can be used for first order differential equations, and I'm going to be doing that at this moment. In addition to that, it's also very useful technique to be able to integrate. I myself, one of my techniques of integration is rather than integrating, I differentiate. So to get my answer, I differentiate and then just sort of solve these relatively easy linear equations involving these undetermined coefficients. So, and many times you can just sort of guess the answer. So a lot of times my technique for integration is differentiation. And as long as you know what a basis is for your particular vector space, everything works. Okay, so undetermined coefficients. Here is an alternate way to solve the equation. So we will give you a technique in section 2.1, how to solve a differential equation that is linear and first order with constant coefficients. This is a different way of doing it, okay? And so a non-homogeneous linear differential equation of first order. So A, solve the simpler equation. So one way of doing something is to solve a simpler equation and then see if that helps you. If that doesn't work, solve a harder equation, see if that helps you. Sometimes making it harder actually makes it something you can actually solve. But in this case, we're going to try to solve a simpler equation, solve the more difficult equation. So just get rid of the b. Just make b equals 0. Call the solution y1. Observe that the only difference between equations 1 and 2 is, therefore, it may seem reasonable that the solutions of these two equations also differ only by a constant. Test the assumption by trying to find a constant k such that y equals y1 plus k is the solution of equation 1. Okay, so compare your solution for part B with the solution given in the text in equation 17. Note, this method can also be used in some cases in which the constant b is replaced by a function g. It depends on whether you can guess the general form that the solution is likely to take. This method is described in detail in section 3.5 in connection with second order equations. Oh, by the way, sometimes we call it ODE, ordinary differential equation, or we call it a DE, a differential equation, or we just don't, if in context it's no, you know that it's an ordinary differential equation, we just say equation. So notice we sit here, a second order equation. So sometimes we're lazy and we don't say, well, it's a second order ordinary differential equation. We just say second order equation. Okay. And later we get in the course, the more we just sort of say that. Okay, so let's do this. So let me get rid of some of this so I can write. Okay, and then the last one. Okay, so we have the following differential equation. So this is method of undetermined coefficients. By the way, the reason that I use this book is that the text is, read the text. It's not the best written book, but the problems are excellent. So the reason for using this book is the problems in this book. The problems in this book are the best of any elementary differential equations book by far. So these have definitely the best problems anywhere. Okay, so so let's do this. So I have, well, D, and I'm going to call it Y1. So I'm going to, instead of calling it dy dt is equal to ay. So I've gotten rid of the b. So I'll just call it 1. So dy1 equals dy1 over dy equaling ay1. Let me write this as a differential form. So dy1 equals ay1 dt. Let me divide both sides of my equation by y1. So dy1 over y1 equals a dt. And let's actually integrate this differential forms. And so I get that the integral of dy over y is just ln y, ln y1 equals at plus some constant c. Let's exponentiate both sides of my equation. And so I get that y1 equals e to the c, I'll call that c, e to the at. Actually, I also absorb in the absolute value the absolute value by the constant c. So I don't need to put an absolute value around y. 1 is equal to. So let's do part B. It was A and B, right? Yes. So let's do part B. So in part B, I suppose that y is equal to y1, okay, is equal to y1 plus k. Well, y1 solves this equation, and where k is some constant, and where y solves our equation 1, our original equation. And so I have that y equals c e to the at plus k. So let's plug in. Well, since dy over dt is equal to, well, let's differentiate this. The derivative of c times a constant is just c times the derivative of that constant. So c times the derivative of e to the at is a e to the at. Derivative of a constant k is just 0. Next, well, let's look at the right-hand side of my differential equation, which was just ay minus b. So this is a times y c e to the at minus b. So I just replace y here by this. And now let's try to simplify. So this is equal to, multiplying a inside the parentheses, ac e to the at plus ak minus b. Well then, my differential equation, dy over dt, equaling ay minus b, then becomes, so that's the original equation 1 that I wanted to solve. So, well, I figured out what dy dt is. It was ac e to the at I figured out what ay minus b is. It's a, okay, well, get control. ac e to the at plus ak minus b. Well, add b to both sides of your equation. Subtract ac e to the at from both sides of your equation. So b equals ak. And so I have that k is equal to b over a. And so from that I get, or maybe I should write it here, that k equals b over a. And so let me plug in. So now I have that the solution is y equals c e to the at plus k, which is b over a. And that is your solution. And it said to compare, actually I never did compare it, but it should be the same. Compare to, here, let me actually look in the book. Let's see if I can get the book here. Here it is. It says, this is, what problem is this? It is undetermined coefficients. These current coefficients. So it says problems, so equation 17, let me check. Equation 17 says y, oh, they wrote the other way, y equals b plus c e to the at. So it's the same equations that they wrote the b over a first. So yes, therefore, yes, it is we did it the same way. And it is a solution. Good.